All right, guys, so today is the time to introduce one of calculus main problems. So of course, turn your cameras on if you're in a situation where you can do that. I would really appreciate seeing your faces and your expressions. This way I know what you're doing, or if you understand or confused, that helps me a lot, okay? So again, guys, remember that I do keep track of who opens the camera and who doesn't, in case that becomes an issue. All right, so here is the tangent problem. So given a curve C, how do we find the tangent line to the curve at that point? Do you understand what that means? So a tangent line is one line that only touches the curve, just scrapes it. And of course, the first question, maybe you would have an idea, guys. Would you care to comment, why is this a major problem? Why would anyone care about such a problem? You just don't go on the street and try to find tangent lines to the curves. In real life, of course. Well, I mean, obviously in real life. I mean, I'm not sure how you distinguish real as opposed to fake life, but I mean, be my guest. Any ideas, guys? Why would you go about doing that? Yeah, but again, to show the slope, but why would you care about the slope of the graph at that point or anything of the sort? Well, whenever I remember this question, I remember to my young warm days, right? You go to a bar and you look at a pretty girl and you say, baby, may I lay tangents to your curve? May I be your derivative, right? And of course, she should know that you are a guy that knows what he is doing. That's one reason that you might care about tangent problem. The other reason you might care about the tangent problem is that if you care to investigate a curve, here is a curve. We will see shortly why we might care to investigate what sort of curves there are. The simplest instance of a curve is a line. Do you agree? If you think, look at it. What makes a line so simple, guys? You see, I'm holding one point with one hand and I'm holding another point with my other hand. Do you see that? Now, do you see that as I move those points, you can imagine this invisible string connecting them? What does it say? It says that between any 2 points, there is one line. It means that if you specify exactly 2 points, you will have a line, okay? So that's the simplest curve you can have because you need to specify 2 points. What do you think would be the next simplest curve when you have to specify how many points? A line is determined precisely by 2 points. Here I'm holding 1 point, here is another. You know it's determined by 2 points because you can, I assume, imagine where the line is. You see, I'm doing those gestures. You can imagine I'm holding a small string, which means that 2 points are sufficient to decide what a line is like. Good? Now, what's the next simplest curve after a line? What do you think? How many points do I have to specify? 3. Right? 3 points. Now, a parabola goes through 3 points. You understand? If you tell me 3 points, quadratic is determined by 3 points. Cubic is determined by 4 points. So specify 4 points, I can give you any cubic. Specify 5 points, I can give you any quartic, any degree 4 polynomial. You understand? So there is a hierarchy of how simple is the curve based on how many points are required to immediately figure out what that curve is. Understood? So that's what we do here. Now, why would you care to? What do you care to do in calculus altogether? As I mentioned, guys, that's a very good idea to keep track of your goal. What is calculus about? It's a very, very powerful idea that you see all the time, and that idea is that you can build complexity out of very simple building blocks. So when you try to describe some particular phenomena, you try to find the simplest occurrence of that phenomena and describe everything else in terms of that occurrence. So if you are trying to describe a curve, you will pick the simplest occurrence of a curve, which is a straight line, and try to describe curves, as I do in the picture, as a chain of straight line segments. You see that? Here, of course, I made them rather large so you can see that. But if you break the line segments to smaller pieces, the chain will be tracing the curve much better. That's how you use, that's what you use in computer animations or computer graphics. When you're playing video games and you see, this hero, this persona that you're playing, and it looks realistic to you, it's actually built up of tiny triangular tiles. And the motion of each triangular tile is very simple. That's the mesh, right? It's very simple, and the complexity arises from just having to repeat this calculation many times. Okay, so that's an application of calculus. You build a complicated figure out of triangular mesh. Good. And in linear algebra, you can understand how you can morph triangles, what you can do with them and whatnot. So in general, that's the general philosophy, is that you're trying to study something, you build it up from simple instances. So when you are looking at an image on the TV, it's made of simple pixels, right? So very complicated. Any movie, anything that you're watching is made of pixels. That's an idea here, right? We make out of different colored pixels an image. Sound waves can be constructed by a superposition of sine waves. The simplest wave that you can generate mechanically is a sine wave. You can just take a rotating drum and you can rotate it at regular intervals, and you can generate a sine wave. And if you can generate sine waves of different frequencies, in other words, faster, slower sine waves, you can superimpose them to create complicated motion. And I can show you videos on that. Good. Now, if you study areas and volumes, you can think of area and volume as, let's say, area as built up of rectangles, because rectangles are very simple. That's the second part of this class, or at least the beginning of it. Calc 2 examines the area problem much more vigorously. But the idea is you are building up the complicated shape out of small thin bars, and you add up the areas of those thin bars to approximate the area of this complicated shape. Okay, now why specifically do we want to focus on tangent lines or lines? So if you think about Newton's laws, look at it. Here is a rocket. It flies in some complicated pattern. You see, if it does not fly in a straight line, it means that there is a non-zero net force acting on it. There is some non-zero force acting on this rocket, because an object that is not acted upon by a force, or the net force is zero, will always travel in a straight line at constant speed. Okay, and now imagine that this rocket is powered by this engine, and at this moment the rocket turns off the engine. As soon as it turns off the engine, it will fly away from its path in a straight line. You understand? And that straight line will be touched at the tangent to the curve. So in German, the word for derivative is actually much nicer. I like it far better than in English. It says, it's called Ableitung, which means lead off. It's a lead off. The derivative is the lead off. And it reminds you that here is the curve. And when you're departing from that curve, you're led off that curve in a straight line. You understand? Always think about the humble origins of any idea, and then you can understand it. Avoid, if somebody is fancy, maybe this fancy person is a peasant's son. Try to understand the humble origins, and you understand that person. Good. Now we will see that the tangent problem is instantaneous velocity. We started this class by trying to compute how fast a car is traveling at a given moment. Remember, instantaneous velocity, what the speedometer is pointing out. Mathematically, finding the tangent to the curve, that's geometric version of that same problem. They are identical mathematically, you understand? The tangent line, the slope of the tangent line is identical to instantaneous velocity if you give the right interpretation. Okay, now if you see, and of course, guys, when you are thinking what is an idea useful for, you have to not think, you know, in the short range. If this is your viewpoint, you are not seeing anything. You understand that anything that's very useful and very incredible, it is a very complicated chain where the end result seems naively to have nothing to do with, and those are the most interesting special results, is that when you realize that this thing that you are seeking is entirely underneath your nose, you just could never recognize it, or because it does not look at all like what you are searching for. Okay, a sort of, if you remember, you have seen Indiana Jones, correct? I've actually met just recently an American that apparently has not seen Indiana Jones. That's very surprising. But you know the movie, correct, guys? You've seen what happened with the Holy Grail episode. When you have a lot of those fancy grails, they look so shining and so impressive, but the Holy Grail is the simplest of them all. And that's exactly what you should think in mathematics, is that, you know, the ideas that are truly dazzling, they don't shine. Okay? And here is a small example of what I mean. So in the, I think, 18th century, a mathematician named Buffon, for instance, came up with a very funny way of calculating or measuring what is pi, right? By allowing nature to tell you what pi is equal to. You know, when you press in your calculator, pi is 31415 and whatnot, right? It has a bunch of digits coming out, right? How do you actually calculate it? So here is one thing that you can do, guys. You can take a ruled piece of paper, and take a needle that is as long as the lines in the paper, and just throw the needle on the ground and count how many needles intersect a line, intersect the ruled paper. Maybe I should show you the video if I can find it. Give me a second. I'll show you maybe in YouTube. Here, guys. You see this? So you see those needles? Now he makes the distance between the bars, between the lines of the ruled paper, to be 2 needles long. And what you do, you scatter those needles randomly, like this. And then you count how many of those needles very patiently intersect the line. You see? You've seen it? Wonderful, isn't it?
In this segment, we will look at the...
Isn't it amazing, guys? Were you impressed? You might still think, oh, why would I care to throw needles? But then again, you're not seeing my point, right? My point is that very, very unrelated results, it seems, right? It seems, I mean, what does it have to do with the tangent to the curve? But in a long chain of events, it has much to do with the tangent problem. You understand? My point is that very unrelated, seemingly unrelated things have to do with that idea of finding the slope of a tangent line, which we will try to understand. And here I actually show you how the calculation is carried out. You will not understand it. You need to go through a lot of ideas in calculus to see what that works. And in probability, I explain that later in the semester in probability, okay? So that thing you need integration to understand, but integration is the reverse of differentiation, of derivative, and derivative is finding the slope of a tangent line. Okay, so that's just not the most long chain. You see, it's still somewhat related to mathematics, but imagine, I mean, whatever you seek, right? If you seek for El Dorado, if you read Edgar Allan Poe, ride boldly, ride over the mountains of the moon, down the valley of the shadow. Ride boldly, ride, the shade replied, if you seek for El Dorado. That's pretty much what I mean, is that if you want to understand something very, very deeply, you will have to travel a very long and complicated path and be patient, very patient. Good? So now let's consider finally what is that tangent line problem and try to understand it. So it's very easy to define a tangent line to a circle, because if you take a line and a circle, either the circle and line do not intersect at all, or in general they intersect exactly in 2 points. You agree the line crosses the circle in 2 points, or in rare events the line intersects the circle in 1 point. So the tangent to the curve is defined as, to the circle specifically, is defined as the line that intersects the circle at 1 point exactly. Good? Now, there is, of course, a problem with that definition if we want to find the tangent line to a curve defined as y equals f of x. Do you see that this line intersects the curve at 1 point, but it's clearly not what you mean by tangent. It doesn't seem like a gentle touch. Tangent means you're doing this, right? You're petting the curve. You're not piercing it through. So how do we come to the idea of the tangent line? What can we do there? Okay, so first, guys, I'm not sure if you remember what is a line and what is a slope. So because of that, we will make a short review of that. Okay, so before I comment, let me see how you would answer it. Guys, if you had to explain to somebody what is slope, what does it measure, right? You can give me both the formal definition and also hopefully some of you can try to convey what's the idea. So yes, I expected 2 people say right away, rise over run. Rate of change is vague, but why rise over run? What are you trying to communicate when you speak of slope? Okay, guys, that's more interesting than just remember it. So slope, but what is a slope? What are you trying to communicate? Well, I'm not sure if the line moves. The line is just stationary when you calculate the slope. So you are showing what when you try to communicate? Okay, change in y, change in x. Simply put, you're trying to express that one line is steeper than another line. Yes? So this line is very not steep. This is more inclined, this is more inclined, and more inclined, right? So you're trying to express how steep is a particular line. Very good, steepness. Okay, now what is steepness, guys? It's obviously a qualia. It's something that we feel, but we can communicate it this way. Notice that if I have a line, you draw a line, look at it, guys, and I select any 2 points. I select, here is a pair of points, here is another pair of points. I label them as little ab and capital AB. Do you see that if I use that side of the line as the hypotenuse of my triangle, the triangles are similar? Do you see that? Do you understand what similar triangles are? So I have 2 similar right triangles. There is the big blue right triangle and there is the red right triangle. And they're similar. Now, would anybody explain to me what is similar? Similar, guys, look at it. It's this idea. If you want to make something similar to me, but bigger, you will grow my nose, you will grow every feature, but they will stay in the same proportions, right? You understand? So when you calculate rise over run, you're calculating the proportion of the right triangle, which stays the same if you have a similar triangle. So you see similar triangle, you have a bigger rise over a bigger run, right? If the rise is increased twofold, the run will increase twofold. If you halve the run, you halve the rise. You understand? So that's the idea. The idea is very primitive and yet somewhat complicated. You have to understand the idea of similarity. You with me, guys? So what the slope is communicating is the ratio of the vertical to the horizontal side of the right triangle that is thus formed. And anywhere on the line you form that right triangle, you see, I mean, it's a bit intuitive, I hope, right? You see that the line will make constant angle with a horizontal line and constant angle with any vertical line. So that means that the angles of the right triangle are the same, which means the triangles are similar. And that means that the slope anywhere you calculate it is constant, okay? And now if you have a short run and a very long rise, that means your line is very steep. It means just move a little bit horizontally, you have to climb a lot up. And that's what the slope communicates. So a very big slope means you, for every small horizontal motion, you have to execute a huge vertical motion to stay on the line. Good? It's kind of breaking the motion on the line. You're moving on the diagonal, it breaks it into horizontal and vertical motion. Do you see that? Okay, guys, it has to be, the slope has to be extremely intuitive, because if it is, you will understand most of the semester. And this is what this M is measuring, okay? Now I can use that information to figure out that what is the equation of a line. Now the equation of a line, even if I'm blinded to it, so if I select a point XY on the curve, okay? If I were to select some point here, let me place it in orange. Here is a point XY, right? And if I use XY and the point AB, if I use this, I would obtain the same slope. So if I use the slope, let's say this point, so for simplicity is AB, and the other point is XY, any XY on the line will measure the same slope. You understand? That's how it's defined. Any point XY on the line will measure the same slope. If you select a different XY above the line, you will have a bigger slope. If you select XY below the line, you will have a smaller slope. Is that clear? So what you can do is you can say y minus b divided by x minus a measures the slope b, which means that y minus b equals to m x minus a. And that gives you the equation of, not the equation, but an equation of a line. Yes? Do you understand what there is a picture there, guys, but I hope you understand that without a picture, if I know the slope of my function and I know a point on my line, then I'm able to compute that equation of a line. Yes? So for instance, guys, what would you observe if I pick this point? If I pick this point XY below this line and I still use that point, what would I calculate? So what's the relationship between y minus b in this case and x minus a against m? Tell me please, what's the relationship? M is that slope of that line. What's the relationship if I select xy below? So here is the question. M is the slope of my original line, and xy was selected below the line. What would be the relationship of y minus b over x minus a to m, guys? Which is are they equal? Are they not equal? Is one bigger? Is one smaller? Tell me. So you have to be careful, guys. Which is smaller than what? I want to be precise here. Which of those quantities is smaller? Is m smaller? Right, m smaller. Okay, xy is steeper, or xy the xy expression is less steep. What do you think? Exactly, xy is less steep. You see, guys, look at it. Look at it very carefully. Less steep because here is that point. Look at it. Look what happens. And here is, if I were to calculate the slope here, I see that I have a hypotenuse that is less steep than the actual hypotenuse, right? That should be there, okay? You understand what happens here? So even if I do not see, if I know the information about the slope and you're giving me a point on the line and another coordinate, I can easily figure out whether the given point xy is or is not on the line, even if I do not see the picture. You understand that? Okay, guys. And here now we come to the any further questions, guys. Let's say maybe I will give you one comprehension check quickly. Okay, so this is a comprehension check here. Tell me please if the point 2, 3 is on a line of slope. 0.23 is on a line of slope 5. Is the point 1, 5 on this line? If not, is it above or below? Above or below the line, naturally, right? So you see what I do, right? So I take this other 0.15 and I try to calculate the slope resulting from a line crossing 1,5 and 2,3. So what I do is I say 5 minus 3 divided by 1 minus 2, right? And I get what? I get 5 minus 3 is 2 and divided by minus 1, so it's minus 2. And minus 2 is less than 5. Minus 2, by the way, means that I am descending. My rise is negative, so it means that this is the actual line going at 2, 3. And from this line, this is somewhere over here is the 0.15. You understand? So without drawing anything, I can just reason using mathematics whether or not my line is, my point is below the line or above the line. I hope that's clear, and I hope you understand what slope means. Very important. Yes, guys? Now, we're back here. So we are going to try to redefine, and be here very careful, guys. We're going to try to redefine what is a tangent line. So we then begin by a secant line. You understand? We're going to try to define tangent line that is local. So we are going to fix a point at A. I want to know what is the tangent line at the point A and to the curve y equals f of x. So what I will do, I will select a point Q, another point Q at some location x, and I draw a line connecting P and Q, and I can calculate the slope, yes? What is the slope of the point Q? The point Q is at location x, f of x, you understand? The location of this point is at x, f of x, it's on the graph. And the other location is a, f of a. And then I calculate the secant slope. So that would be rise, difference of y coordinates divided by difference of x coordinates. But you can see that's clearly not the tangent line because it crosses the curve in 2 points. Now I will push Q closer and closer and closer, you see? Now point Q and point P are closer and the line begins to look like it's touching. And I'm gonna push it more and more and more until it looks like it's 1 point. Let me illustrate it using a video or using some animation of that sort. Okay, guys? Here is that situation. For instance, let's suppose we want to find here is some graph, here is the function, right? I want to find the slope of the tangent line at this point. Yes, so this is my point Q, do you see? I don't touch the point P is here, that's where I want to find the tangent. You see? So now its location, look at it, you see? I'm sliding the point Q. That's my point Q that I'm changing. Do you see it, guys? Now, that's why the point Q cannot be given exact coordinates. You just say that its coordinates are x and f of x, you see? So when x is very close to, let's make this point maybe nicer, maybe let's make this point 0. So here I'm making x go to 0. You see what's happening? And as I make this point Q get closer and closer to that point, it begins to look to you as if those points have been merged. Here you see? more and more merged. Do you see that, guys? I can make it even smaller. There is still distance between them, but the distance becomes eventually invisible to you. So it looks to you like this curve actually passes through one point. Again, the trick. I cannot calculate slope from the point in itself, which is what I need for tangent line. But what I do, I take the point Q, I move it closer and closer and closer. And then when it looks like it's 1 point, I have a very good estimate of a tangent line. This line can, of course, cross the curve multiple times, but locally, you see, locally, it looks like a trajectory of a bullet that grazes the curve. Just touches it, not pierces it through. Whereas if you have a secant, you can see then you have entry hole and exit hole. Here you just make entry and exit holes very close together, and it looks like there is just the bullet just grazed the curve. Do you understand? So guys, one thing that you need to do is understand where the formula comes from. You're not memorizing anything, yes? I mean, you understand the idea is very simple. I'm going to slide point Q towards point P. How am I doing that? I'm making X approach A. So that's my definition of tangent line. It's f of X minus f of A divided by X minus A. Limit as X goes to A. Let me ask you a few questions to check for comprehension, guys. What is X comma f of X? What sort of point is that? Perhaps my question sounds very vague, but I'm hoping you are understanding what I mean, right? You can use the analogy of the bullet, okay? I want to find the tangent at the point A, f of A. In other words, there is a graph. There is the x coordinate A and the y coordinate f of A. Why do I pick the point X, f of X? What is that other thing? Exactly, so that's the point Q. Okay, so the point Q is not exactly a fixed point, it's a point I slide, okay? It means what this is accomplishing, guys. You see this f of X minus f of A is the rise, is the change in altitude. X minus A is the run, it's the change in X displacement, yes? So when I make X go to A, I will make f of X, if the function is continuous, go to f of A, right? And what I will have is I will have the tangent. All right, let's see if you can actually carry this process without my explanation. Guys, I want you to find the equation of the tangent line to the curve y equals x squared at x equal to 2. So do you understand what I'm asking, guys? You see, there is a curve. You can possibly draw it if you want to, but it's not what you should really, drawing should only assist your thinking. You have a curve. You want to find tangent to that curve. So you need to find the slope of the tangent line, yes? So you imagine that the curve, and there is at some local point, when x is equal to 2, you want to know what's the slope. How do I do that? Yes, but Humira, why? But Francis, I can draw it, but again, it's invisible. You have to understand. So it's not y equals to 4, no. Y equals to 4. You see, my point is, guys, imagine you're blind. And mostly you are blind when you deal with mathematical objects. They're too complicated to visualize. What you're trying to do is figure out what exactly you're feeling it. What exactly are you gonna do? You don't need you don't need the eyesight for that. First, ask yourself, what do I need to calculate slope? I need 2 points. Do you agree? 2 points. And 2 points meaning 1 point having 2 coordinates, another point having 2 coordinates. You understand? When I say point, I mean point in the plane. So here is what we have, guys. So we need to calculate at x equal to 2. Now, what is the coordinate at x equal to 2? The coordinate at x equal to 2 is 2, 2 squared. You understand? That's if the x coordinate is 2, the y coordinate has to be 2 squared. And therefore, this is, you can just keep it as 2 and 2 squared, or if you want to, you can write 2 and 4. But I would advise avoiding doing that, doing calculations when they are not necessary. Okay, in this case, squaring the 2 is not necessary. So it's 2 squared. So to find the slope, you need to take another point. Tell me what other point will I take. Now I want a tangent slope. So in other words, I want to take the other point very, very close to the point 2, 4. Do you agree? You see why very close? If you've seen the drawing, here is the point 2, 4, whatever it's located, and here is the other point. I want the other point to essentially be merging with the first. So for that reason, I will say that the other point is of an unspecified variety, but if x is the coordinate of that point, what's the y coordinate? Help me. X squared. Do you understand, guys, what the equation y equals x squared means? It's very simple. It means that if you have a pair of coordinates, the second coordinate is the square of the first. Okay, guys, x is a myth. There is no such thing as an x. It just means that we have points of the form number is the first coordinate. The second coordinate must be that number squared. Okay, when I say y equals x squared, I'm saying the points that are lying along this curve are of the form number, comma, number squared. So I will see 2, 4, or 5, 25. You understand? But I will not see 5, 7, because 7 is not the square of 5. Good? So even without knowing what the graph looks like, even though it's easy in this case, it's a parabola, I can imagine what it means to be on the graph, what it means to be on this curve, and what it means not to be on the curve. Okay, so I have those points. I have x squared, and 2 and 4. Now tell me, what do I do with those 2 points? Why would I want to plot them? Slope. In particular, what do I do with that? So I measured, you understand, guys, it's very easy. Look at it, 2 points. I want to calculate the slope between those 2 points. 2 points determine a line. Calculate the slope between them. Yes, use the slope formula. Do you understand the slope formula, guys? You just kind of said a moment ago that you do, or at least some of you did. So very simply, you write this. You write the y coordinate minus 2 squared, right? The difference of y coordinates divided by x minus 2. You understand why I did this? Okay, wonderful. Now, what do I do next, guys? I don't want just any point x squared. I want x squared to be very close to 2 squared, yes? So I want the x coordinate to slide towards what? So I take limit where x goes to what value, please? 2. Make sure you understand it, guys. Very important. Do you understand what's happening here? It's entirely natural. It's not I memorized nothing at all. I just understood what is my goal. My goal is to find the slope of a tangent line. Do you understand the philosophy, guys? Now, I'm not sure what a tangent line is, but I see that if I select secant line, in other words, if I select one point on the graph, another point on the graph, there is an entry and exit wound. An entry at 2 squared and exit at x squared. Yes? There is basically the line intersects the curve in 2 points. I want the line to intersect the curve in 1 point So what do? I slide the other point towards the first. And that looks like it's intersecting in one point. Again, guys, do you see that picture? Here is that picture. Do you see? Here are 2 points. Doesn't matter of what graph, right? 2 points. I can slide the graph towards this point and thereby make it look like it's just 1 point at all, right? Just 1 point. Good? You understand? Now help me calculate it. You see, I mean, just by logic, I'm able to figure out what I'm searching here. So the limit becomes the slope m, exactly. The limit is the slope m, because in the limit, the 2 points merge. So then it's very easy. Then I factor, it's 0 on the bottom, right? So I factor it out. So I write limit as x goes to 2. And here the numerator I factor and write it as x minus 2, x plus 2, divided by x minus 2. And now, because x minus 2 is not a real 0, they are not actually the same points, I can just cross them out. And the result is, simply 2 plus 2, which is 4. The result is 4. You agree? So I just figured that my slope of the tangent line is 4. Now, and I also know a coordinate. So look at it. I have the coordinate 2, 2 squared, or 2, 4, and slope equal to 4. If I have a point and a slope, I know everything about the line. Yes? You agree? Now I can write an equation. Exactly, Humira. So the equation is y minus 4 equal to 4 times x minus 2. Brilliant. Now let me just elucidate it a little bit again. Here is that same limit calculated. The limit is 4. We have, you understand why I have y minus 4 equal to 4 times x minus 2? It's just what I'm saying is that now I'm using the xy. I'm saying if xy is on the line, I'm changing the meaning of xy, right? If the point xy is on the line, then if I measure the slope from xy to the point 2, 4, I should obtain the slope 4. And that's the only way I can be on the same line. Do you understand? So this equation, I mean, somewhat more natural to think of it in this form, right? I have y minus 2 squared, that's the y coordinate on the graph, divided by x minus 2 should equal to 4. Now I'm just using the idea that I already know what's the slope of the line, and I know the line goes through the point 2, 2 squared. So any point xy that goes on this line, it must have the same slope if you measure it this way. Yes, you understand? And that's how we got this equation. Just multiply both sides by x minus 2 and you have this equation. Are we clear? You let me know, guys, if you're confused. It's not just this calculation, you see. It's understanding this concept. You have to be it has to be so obvious to you what is the slope of a tangent line, what is the calculation meaning, that it doesn't even take, forget about useful or not useful in real life. It's just so obvious that you don't even have to think about it. You understand? It's just so obvious that that makes sense, this calculation. Of course, we will do another one. So here is another one, guys. Now, notice that doing this process all the time for different numbers, it's annoying. You can solve many problems simultaneously, or all the problems for the curve simultaneously. And that's what I will ask you to do here. So suppose that we have this function equal to minus 3x squared plus x plus 5. And I want you to calculate the slope of the tangent line. In fact, write to me the equation of the tangent line, not just the slope. I want you to write me an equation of the tangent line at the point x equal to 1. And then I ask you, can you write it at any arbitrary point a, f of a? Okay. Can you do that for the instance when x equals to 1? And in general, can you just do that for all possibilities? Any a, f of a. Go ahead, calculate, please. Well, it's all about, Francis, about communicating meaning. F of x is just some generic point. I mean some specific point here, right? It's just a matter of communicating meaning. So first do it for a particular number and then see if you can do it for an arbitrary number A. Class ends at 3:30, am I right? Ready? Well, yes, it means that you should have the answer, guys. It should be very fast when you solve it. So here is what happens here. So first, my question is to find the slope at x equal 1. So what's my full point? My full point is 1 comma f of 1, which is 1 comma 3. Yes? So what we have is this. We have f of x minus f of 1 divided by x minus 1, limit as x goes to 1. Everyone set the equation this way, because you understand what that's supposed to mean, right? So x f of x is the second coordinate, the coordinate of the point Q that you will slide towards the point P, at which you want the tangent. Here it is, yes? And so once you have this limit, okay, we'll see in a moment, Jahin. So once you have that limit, x going to 1, this is my function, minus 3 divided by x minus 1. When you simplify it, it's minus 3x squared plus x plus 2 divided by x minus 1. Good. And then I can factor it out. I need to get rid of x minus 1. The factored out version is minus 3x minus 2. Francis, I'm not sure. Where do I have? Where do I get what? This? It's just my function. My function was minus 3x squared plus x plus 5. So I take this function, subtract the value of the function at 1, which ends up being 3, divide by x minus 1 because I'm searching for the slope at 1. So I take the limit, I factor it out. I cross away x minus 1 because that's approaching 0. And I have limit of minus 3x minus 2 as x goes to 1. And that limit is minus 5, which means my point slope form of the equation is y minus 3. That's the y coordinate, right? The y coordinate is 3, equal to minus 5 times x minus 1. Now it's much easier to understand what I did if you actually do it in general. Suppose I want to know what's the slope at a general point a, f of a. So I do f of x minus f of a divided by x minus a. Good? This is my function. This is the function evaluated at a. Where are you lost, Francis? This part of the equation, do you see it? Forget about what we did before. We can just do it in general, and then you should be able to see what's the solution, if you can think of it generally. So in general, if I were asked to find the slope at the point A, that means my full point is a f of a. Everybody says that? I mean, I'm sure some of you are asking because you don't remember how to factor. You're asking, how did I factor it? Or how did I, you understood the previous setup and you understand that in theory I could factor it. And if I could factor it, that would work. Now I'm showing you how to think of it much better. One mistake that some of you do is you do many calculations. Like over here, I bothered and I said that f of 1 is equal to 3. If I were doing it for myself, I would not bother with that calculation because this is what I do. You see, I just say f of x minus f of a divided by x minus a. Do you see that this is the what is f of x? It's what the function does to the input x, and here it's what it's doing to that input, and minus what it does to the input a. Here it is. Yes. Now what I can do is I can group like with like. You understand? I group the square with square. I group. Yes, I group the x with the x, and the constant with the constant. So look what happens when I subtract. It would be minus 3x squared minus minus 3x squared. Okay, so it's like this. Let me show you slower. Here, I will group it. So I will write minus 3. It would be like this: x squared minus a squared. That's grouping this and that. You understand? just what you have is, look at it, just factor out the -3. Just group them and factor out the -3. It's always going to be a constant times x squared minus, it's always like that. The next will be plus x minus a. And the next is going to be 5 minus 5. Okay? I will show you afterwards maybe just a longer expression, and you will see how that at least will look before when I group them together. Okay? So, and then here is that expression. Here is what survives. Good? This is what survives. Now I can factor x squared minus a squared into x plus a, x minus a. Agreed? And this I just keep as x minus a. Now in this expression I can factor out x minus a. So look at it, factoring it out, I'm left with -3 x plus a plus 1 times x minus a. You see I took it out. Here it would have been distributed right in. Look at it, it would have been distributed here and here. So you can see that's correct factoring. Plus 1 because look at it, I have to have -3. Look at it, what is that expression? It's -3 plus 1 times x minus a. What do you mean? Where's 2x minus a? So there is this. Look at it, there is this. And in here you see the digit 1. So when you factor it out, it will be a 1 naturally. Right? So it's x minus a multiplied by 1 in here and by this in here. So when I factor it out, it looks like that. Good. Now I can cross it out because x is not truly a, it's just approaching a. And when I cross it out, look what happens, guys. Look what happens. X approaches a, so we have -3 times 2a now in the limit, right? X now becomes like a, so it's -3 times 2a and plus 1. So my slope is simply -6a plus 1 at any given number, -6a plus 1. Good? And so what's the equation? The equation is y minus the y coordinate, which is written this way, is equal to the slope times x minus a. Now look at it. If a were equal to 1, I can just replace it. If a were equal to 1, it would be -6 plus 1, which is -5. The slope would be -5 at 1, right? And this would be then x minus 1. And here I can plug in 1, so it will be -3 plus 1 plus 5. Right? You understand? So I can just obtain this general equation and I can plug in any value afterwards. And I have the general form. And when you think this way, at least it's easier for me actually than to think of concrete numbers, to think of general numbers. Much easier. I'm not sure why it's otherwise to many people, because I just think, okay, here's a number, here's a person. It's much more malleable, and I can solve all the questions right away. I mean, if involving this function, I found all slopes of all tangent lines and all equations of tangent lines at any points at once. You understand? So I solved it right away. Here is another question, guys. Let's see if you can do this one. Find the tangent line to the curve y equals root of x at x equal 9. Well, Francis, think about it. What do you need to calculate a slope? You need two pairs of points and another two pair of points, right? That's where you start. Okay, Humira, let's see if you're right. Yes, you are. Okay, wonderful. Yes, very good, guys. So very good, Humira, very good, Tzvi. Guys, you understand when you ask yourself how to start, make sure that this is what I do, right? I mean, I don't try to remember what somebody did. I try to say, okay, what am I really trying to understand here? So there is a curve and I want to calculate a slope of the tangent line. What is a tangent line? It's essentially a line that goes through the curve at 2 points, but where one of the points is very, very close to the other, okay? So one point is the point P, which has very definite coordinates. In this case, coordinate is 3. Sorry, the coordinate is 9 and 3, correct? So I want to find it at x equal to 9. I'm just specifying, I'm just lazy here, and I'm specifying only the first coordinate. But the full point is 9 and 3. You understand why that's the full point? Because if x is 9, y is the square root of the first coordinate. So that must be 3. Good? And another point can be given by coordinate x, and the second coordinate is root of x. Do you agree? So that's the general other point, which I don't want to give numbers to because x will be very close to what number? So then what do I write here? I write root x minus 3 divided by x minus 9. Yes? And then how do I make sure that the point x, root x, approaches to the point at which I want to calculate slope? What do? I take limit, right? I say limit as what that goes where? All right, write in the comments. Limit of what to where? X to 9. Do you all see that? Only few of you react. I'm hoping if you don't react, you think it's obvious, guys, right? X to 9. That's all I need to do. And then, of course, that's the setup. If you understand how to make the setup, you already won half the battle. But not just remember it, guys. If you memorize it, you will forget it. It's not what we're up to here. At least not me. I'm not sure what's your goal. Maybe your goal is just to survive in one piece from this class. But my goal is to hopefully make something stick and make something interesting and understandable. So here it is, guys. Right? It's root x minus root 9 over x minus 9. And so you might consider doing the following. Right? What is 3? It's just it's root of x minus root 9. You might consider multiplying by conjugate. That's one possibility, right? So whenever you see root minus something else, you want to get rid of the root. So you multiply by root x plus 3 and divide by root x plus 3. You understand again what that step was taken, right? I did not care to divide by root x plus 3. I just did it to balance and keep the equality true. I cannot change my expression. So I really multiplied by 1. You understand? So then we can multiply root x times root x. It's basically it's a minus b times a plus b is a squared minus b squared. So root x squared is x minus 3 squared, which is 9, right? And so we have this x minus 9 over x minus 9 over root of x plus 3. So we can cross x minus 9 and push in the limit. And that then we get 1 divided by root 9 plus 3, which is 1 over 6. Because it becomes 3 plus 3 on the bottom. Clear? It wasn't hard, yes, guys? I mean, right? How long does it take to do that? 1 minute. Once you train enough, you should do it in a few seconds. Okay, it's fine. You're just learning it, but you understand. So that's the slope. You understand what we calculated? We calculated rise over run. We calculated slope, and that's our slope of the tangent line. Now, what's an equation of the tangent line? We know that we have one coordinate, which is 3, 9. So it's y minus 3 equals to 1, 6, x minus 9. Good? Okay. And now let's do this one. Last problem, guys. So a particle moves so that its position at time t is x of t equal to 2t squared minus t plus 1. I want you to tell me what's the velocity at time t equal to 1 before you leave. What's the velocity? Remember, we did this type of problem at the very beginning. By the way, no shortcuts if you took calculus before, right? There is a point to what I'm doing. If you do it by definition, you will eventually know how to do it much faster than with some shortcuts. All right, 2 people. So Humira, you're saying 3. Okay, Jahin, what are you saying? Would the equation from the limit be? Yes, very good. Yes, Jahin, that you did very well. That's right. So if you want to, after class, we can solve a few more of such problems where you can have a little bit more time if you want it. So here, let's solve it together, guys, okay? So again, look what is velocity. Velocity is displacement divided by difference of time. Okay, and remember the idea that we had for velocity. It seems like it's a different idea. It feels like a different idea, even though the result ends up being the same as finding slope of the line. Look at it. X of t minus x of 1 is change in position. Divided by t minus 1 is change in time. And why do I push t towards 1 in this case? Could you explain to me? Remind me, why push t towards 1? What's the philosophy here that I'm thinking about? You see, I get the same formula, but a different philosophy, so it seems. Instantaneous, but yeah, so what's the idea? The idea is that, tell me, anybody will tell me the idea? Why in this case, I ask for the velocity. Why do I push? It's not a tangent line. It's not like I want the points to be close together, right? I just want the velocity. Why do I push t towards 1? Why as t goes to 1? Why? Why? Simple question, guys. Why? What limit? I mean, it's going to find the limit. What are you trying? What is your philosophy? What is it? Why do you push t towards 1? Has nothing to do with slope. At least mathematically, obviously, it's the same thing. But what impelled you to take limit as t goes to 1? So why move? We wanted at time 1, but why move the t towards 1? A lot of time, a lot of change. Very little time, very little change. Do you understand? So I want the time difference between 1 and the other moment to be very small, because that means that there was little change, and that means that there was little chance to change speed. You understand? That's the philosophy behind it. If you don't understand the philosophy behind something, guys, it's meaningless, right? You could find the limit, then you forget because you don't care to find the limit, right? It's very simple. Little time, little difference. More time, more difference. In the limit, you have very little difference. And therefore, in the limit, more less and less and less, and that's how you get it. Do you get it, guys? That's how I think. That's why I remember it. Good? Yes, the least amount of time for change, because you're hoping, that's your idea about time, that if you have very little amount of time, then there will be little change, little difference in the velocity, so it will be essentially constant. You follow? And so philosophically, or how you feel about it, it's a different formula. But look at it. Actually, it ends up being mathematically the same as the slope of the tangent line. Mathematically, this formula looks exactly like the one we do for slope, even though what brought it about seems to be different. This formula x of t minus x of 1, because it's difference of position divided by difference of time. In case you're moving at constant speed, that indicates how much distance you traveled in that amount of time. So then you push limit as t goes to 1. You can factor this thing out, and you get that the velocity is 3. Do you understand? Very different feeling for the concept, but the same result. All right, then. So I will stop this lecture. If you want to do more practice questions or talk a little bit, I will wait. Good? If not, then see you on Thursday or in my next class.